Okay, welcome. I'm going to get started chairing my own session with a talk by me. AGU has built this latest construct, and it's called a tutorial, apparently. And so the idea here is I'm going to give a tutorial on planetary core dynamics. And at this, yeah. Anyways, I'll just start doing that. Hi, I'm John Arno, and here we go. So, let's see if I can get this to work. That didn't work. Hello. There we go. So, all right, let's get started talking about planetary core dynamics. What comes out of the core? Well, the big thing that comes out of Earth's core is the magnetic field. And what you can see in this movie is Earth's geomagnetic field on the surface of the planet over about the past 400 years. You could see it's axially aligned with field coming out of the southern hemisphere and wrapping around to the northern hemisphere. Laser pointer. I got to talk to the chair. Where's the laser pointer? Ah, okay, thank you, chair. And then wrapping around and coming in back in the northern hemisphere. And this is generated by flows of liquid metal in Earth's outer core. And that's the surface field, but we can actually extrapolate the field down to the core mantle boundary and see a lot more structure and see a lot of dynamics. And what I want to get across here is that what a dynamo does is it converts kinetic energy of the motion of the liquid metal into into magnetic field energy. And that's exactly what we have living in Earth's core. It's a turbulent dynamo. Okay, so this is a very complex system. It's very remote, and we have limited data. And so that means we need good forward models. And what I'm going to focus on then is how do we build models of the flows in a planetary core that generate the magnetic field? What are their velocities, structures, length scales, and just how do they work? This is a tutorial, so that's the idea. How do things basically work? So first, what drives core flow? And the essential answer is that in Earth's core, it's buoyancy-driven convection. So I have a laboratory demo here, tank of water, shown right there. It's about 15 centimeters deep. You can get a feel for the scale because I put a piece of paper in the background, so the lines on the paper give you scale. I put some green dye at the bottom of the tank. That's going to trace the flow. And there's a heating plate below the water. And when I turn on the heater, the water at the bottom heats up, and it starts to convect. It buoyantly floats up to the surface of the layer. That is buoyantly driven convection. So when we look at Earth's core, I've cut out the mantle. We're just looking at the core. And when we look inside the core, we have a growing solid inner core over time. And it is releasing both chemical buoyancy as well as latent heat of formation. So there's thermochemical buoyancy being released here. So in a simple universe, we have a radiogravity field. And as we release that buoyancy, we should then get convection coming away from that inner core. Does that make sense? Is everybody with me? I feel like we can get personal at this number density. Okay, so very nice. However, I skipped a lot of the good stuff. I skipped the rotation and I skipped the magnetic field. All right, so let's start worrying then about convection in a rotating core with magnetic forces. And the first way we'll get a view of this system is by looking at numerical models, planetary dynamo models. And here's a very nice solution from Andrei Sheko. And this is showing an axial slice. So here's the rotation axis in his fully spherical model. And we're taking a vertical slice through that model. And this shows the radial velocity field in that solution. And this is a dynamo. There's also a strong magnetic field, but I'm not going to show that. And what I think you can see is that the flows are axially aligned. So the flow structures, you could think of the high velocities being shown in red, and they are all roughly aligned with along the direction of rotation. And that means that the flow is rotationally dominated. This is called quasi-geostrophic flow. And we now, in about the past 5 years, suddenly, I would almost say discovered, that rotation dominates these systems in all these dynamo cases. And so you have to find very special cases to find solutions where the magnetic field is fundamentally changing the flow fields. So at 0th order, we can just talk about rotation and Coriolis-dominated solutions. Mike Hawkins first showed this in 2015, and then a number of other papers are now finding this following, and we'll continue to find it. Okay, so that's great. We can now cut out magnetic forces, which is immensely relaxing and makes our job a lot easier. We'll cut that out, and we'll worry about convection in a rotating core. There we are. Here is a nice solution, also numerical, from Thomas Gastine, where he's run rapidly rotating convection. So there's a rapidly rotating spherical shell of fluid, and he has no magnetic forces at all. It's not a dynamo, it's just rotating convection. And now we can get a nice view of the flow structures in his model. And what do you see? You again see the structures are very well aligned with the rotation axis. And maybe you could see at the top surface that there are little swirlies. They're little swirled structures. This is the temperature field. And so the temperature field is getting swirled around, and beneath each bright swirl, there is, in a sense, a stalk going not exactly straight down, but roughly straight down. So that's fundamental to understanding what's going on in these planets in these rotationally dominated solutions, and that's what we're going to try to figure out really for the rest of today. I just want to explain why all these models look like this, and I really won't even talk about the magnetohydrodynamics. Let's first figure out the dynamics of rotating flow. All right, so how am I going to do it? We're going to do that with lab models. And so the first one I'm going to show is from Joule. So there's UFON on the right. This is Rob, that's me in the middle, I think you might notice. Rob Teed's in the back. And this was Rob's last day visiting UCLA for about 6 weeks doing a project with Joule. And there's Joule front left. And Joule has built a very nice device in the lab. It's a cylinder, I think you can see. So it's a funny shaped planet. It's a right cylinder, it's heated from below, it's cooled from above so that the fluid convects, and the whole thing rotates. So the whole thing rotates, yeah. And so there it is rotating in the lab, and she's put a shadowgraph system in front. There you can see it. And so she can image the flow inside her tank. So she's got the fundamental ingredients we need to understand course style rotating convection. And so here are some shadowgraph movies from her. If it matters to you, the buoyancy force has a Rayleigh number of about 4 × 10⁻11, and that's really all we need to know. And the first case is one where we just didn't rotate the tank. And I think you can see it's really messy, massively turbulent flow. Okay, complete mess. It's rather delightful. Now, when we rotate, that's 0 RPM rotation, right? If we start to rotate, then we get this solution, which I showed before. All the flow structures line up with the rotation axis. And I want to point out, importantly, they don't actually stretch all the way across the layer. A lot of people make that assumption, that they perfectly map from one boundary to the other. They absolutely don't in these strongly turbulent, rapidly rotating cases. They kind of break up before, but there is a massive anisotropy in the system. Everything is clearly well aligned by the effect of the rotation. All right. So that at 0th order looks somewhat similar to Thomas Gastine's solution on the left. Okay, so I haven't really explained how that occurs. I've just shown a cute movie or two. So let's try to explain what's going on here. And to really explain it, we don't need lab models. We need really simple lab models. So that's the next step. Simplify even more. And so to do that, I'm going to use a very nice outreach device that we built with Henry Gonzalez and Taylor Launer And I forgot to say, I will be putting links for how to build this and movies for how to build this device on our DIY-namics page that I forgot to put on this slide, and I meant to. I know, I'm a bad, it wasn't good. And in addition, you may not want to build this one, we've also built a Lego table. So it all works on the Lego table as well, and I foolishly missed this opportunity to get the word out to this entire tutorial. Okay, just the same, we've built this very nice table, and guess what it does? It rotates. And that's what we need. It's about 1 meter in diameter and about 25 centimeters deep on that cylinder, and that's all we need as a tool, okay? So you might say that is a terrible model for a planetary core. So let me just argue why I think it's such a good 0th order model for the physics. And I'll do that by looking at or showing some results. First from Susanna Horn at Coventry. She's done full spherical shell models, fairly thin shell, the fluids in this kind of whitish part. And what she's done is she's done the full spherical shell model, but she just cut out, we call it harvested, just a cylinder from near the North Pole. So here's her harvested cylinder. So that is the temperature field sliced out, ripped out of this spherical shell solution. And then she went and she did an actual cylindrical solution. So no spherical shell, no nothing. It's an actual cylinder. And that's the actual cylinder. So the cylinder produces qualitatively the same structures. I don't even care what they are. I just know they're qualitatively immensely similar. In addition, when Rob Teed came to visit and worked with Joule, they took quantitative data. They measured heat transfer versus buoyancy forcing. And here's their lab data in a cylinder. And then Rob did numerical simulations in a doubly periodic plane layer geometry. Matches very well. It also matches very well with previous experiments. And then he did, again, a harvest. He harvested, just like Susanna did, he harvested a cylinder from near the pole, and the cylindrical harvest matches very well with the plane layer arguments, matches very well with the lab data, even quantitatively. So this is a pretty good analogy, okay? And what that means is that Henry is free to keep smiling in this image. This is a good idea, or a good enough idea. So now, let's start playing with the toy models. First, we're gonna do non-rotating flow with a central cold source. For me, that's gotta be a frozen can of crushed tomatoes. It's just how I work in the lab. And it's surrounded by about a 15 centimeter deep layer of water. And so this is not very complex. And let's see what we get. What we get is, here's our frozen can, there's the water, and I'm gonna put in some blue dye. And I'm just dropping blue dye around the edge of that cold frozen can. And what's the cold water next to the can do? Ooh. Oh, I think I did that wrong. Sorry. Let's try it again. Yeah. So the cold water sinks. It's downwelling. So there's a cold downwelling surrounding the can, and it's going to hit the bottom. And when it hits the bottom, what's it going to do? It's got to flow outwards. So then you form a radial outflow. Now, what we can't see is that when this material is flowing down and out, we can't create a vacuum at the top of the fluid layer, so there's actually got to be a radial inflow to replace the fluid that just went down, right? Nature abhors a vacuum. So this stuff has to come in, and honestly, I didn't mark that with any dye, but this thing actually forms a whole overturning cell. And I've simply marked with the blue dye the downwelling and the radial outflow. Everybody with me? That's the non-rotating experiment. Now, let's add rotation, and we're going to add really slow rotation. And because with slow rotation, we can kind of see things well. If we rotate too fast, actually, it gets kind of hard. I'll show you. But we need to start slow. And so now we're using that same experiment, same can, same everything, and we're rotating as slowly as we can with our motor, which is 0.16 RPM. So it's more than a 300-second rotation period. It's immensely slow. And that's great. That's just what we want. And so now I'm just going to put in 1 drop of blue dye. It's going to sink down, and now I need to play with this. And what do you see? What do you see at the top? The fluid's not sinking at the top. It's actually moving off to the right. And actually, it's going off to the right, and then it's going to go into the page. The cross is into the page, the X, and when there's a dot in that circle, it's coming out of the page. So at the top, it's moving faster than the tank is rotating. It's a right-handed system, and the fluid at the top's super rotating. It's moving prograde. Now, the stuff tries to sink to the bottom, and actually it starts to get a little frustrated as it gets to the bottom. It doesn't do a very good job of basically doing a radial outwelling. It's kind of failing. It's doing it a little, but what you see, I'm going to speed it up. Fluid's going around the back at the top. Whoa, and it starts to go the other way at the bottom. So on the other side of the can, it's going in on the other side. So counter-swirling flow. Can everybody see that? Does it show up in the movie? All right. So let's speed it up a little. And what you'll see, oh, the fluid's already come all the way around at the top. It hasn't come around at the bottom, but it will in time. And let me speed this up and see if you can see it. Swirling fast at the top, counter-swirling at the bottom. Good. So that's what happens in a slowly rotating tank. Let's explain this. What's happening is Coriolis is now deflecting all the motions. It's rotating. Coriolis does amazing things. This Coriolis acceleration, and it takes any attempted motions and twists them off to their right. So what's going on? At the bottom, the fluid's still trying to flow outwards. There's still trying to be a radial outflow there. But when it tries to flow outwards radially, it gets curled off to its right. Well, curled off to its right means it's going to continually try to wrap around the tank clockwise, retrograde, going slower than the tank. Does that make sense? Tries to move out, gets sent to its right. Okay, if you do the same argument at the top, well, here it's supposedly trying to have a radial inflow. Well, when the fluid tries to flow inwards, instead it gets deflected again to its right, and it wraps around. So it wraps around the can, but now it'll be going into a prograde circulation. Does that make sense? Good. Okay. So now that's our picture then. And it's interesting. This is the picture we had after, I think this is 4 minutes of filming. And the die really hasn't fallen very far. It's gotten sheared as a muthely, but it hasn't fallen. In contrast, in the non-rotating case, the die was basically on the bottom of the tank in about 20 seconds. So it's not falling very efficiently, and instead it's shearing as a muthely. So why is that? Well, it's because we have induced these swirling flows, which are called thermal winds. And we've got them setting up. You can think of these two hoops of fluid, one going retrograde at the bottom, one going prograde at the top. And what now goes on is Coriolis force now acts on them. So let's look at the top right. At the top right, it's trying to go into the page, but Coriolis wants to send it off to its right. So there's now a secondary Coriolis force pushing radially outwards. If you go to the other side, up here, that's now coming out of the page. If we go off to its right, it's pushing out. If you do the same thing at the bottom, these are pushing in. That one's trying to come out of the page, so to its right means Coriolis is trying to force it in towards the can. And same thing on the other side. So that's really interesting. The fluid, in a sense, is generating these swirls, and then Coriolis acts on the swirls to fight the fluid motions. So the fluid at the bottom is trying to move outwards and radially outflow, but Coriolis is pushing back in. At the top, it's trying to radially inflow, but Coriolis is pushing out. So the Coriolis effects are doing everything they can to fight the circulation, and they're essentially creating what I've falsely called hoop stresses that are fighting the sinking of the fluid. All right, so the fluid fall is being inhibited, and if you went to a really rapidly rotating solution like we have for planets, they're rotating incredibly quickly, and in that limit, you could imagine that the fluid just wouldn't fall, and that is the case. In the infinite rapidly rotating case, fluid won't turn over. And so it's a bit like a gyroscope. Things start swirling around, and they don't fall. And this is actually mathematically the same. There's a nice paper by Tom Hain and a student in BAMS 2013 where they show Actually, the equations are isomorphic. And so let's go look at a gyroscope. That's our analogy. And if we look at this, if I don't spin the top, it falls over. This is a tutorial. And meanwhile, if I spin it, get this, it doesn't turn over, it moves off to the side. So in the spinning case, it's constantly deflected to the side, and it doesn't really lose any of its potential energy. I don't let this heavy material, in a sense, sink. Now, when does it eventually fall? It falls eventually on a frictional timescale. Eventually, there's enough air friction and friction at the pivot that this rigid body slows down, and once it slows down enough, then it can fall over. Okay, it's really important. So, oh yeah, slow-mo, gotta love it. So, that's interesting because planets just keep on spinning. On our time scales, they're not slowing down. And so then the question is, for the fluid inside a planet's core, for instance, how do they convect? How do they turn over? They're spinning super fast. They're incredibly strong rotational inhibition of the fluid motions. So how do they get over this? It's, again, they don't slow down. So we're in trouble. So let's do another experiment. And now we'll do rotating case, but it's now at 13 RPM. That's as fast as this table goes. And so it's going 100 times faster. And the fluid layer is a little deeper, which makes Coriolis even stronger. And I'm now not going to put in my can of tomatoes. I'm now going to spray some dense food coloring on the surface. So it's a distributed buoyancy source, and it's going to form a dense boundary layer that's going to try to sink. Let's see how it does. Okay, there it is. So I've now done that, and what's going on? Is it overturning? No, it's not. Why isn't it overturning? Yeah, let me block out the background. The fluid can overturn on the tank scale. It's too good of a gyroscope. And in addition, it's not slowing down because we've got the table plugged into a battery, right, into the wall effectively. So like a planet, our system's not slowing down. It's a forced gyroscope, and we've now got this dense stuff at the top. How do we get it to convect? We can't slow it down like a spinning top. There's no friction to speak of. We've got this thing powered. So how do we beat this? With a top, you beat it in time. You let friction slow things down over time. What do? What we do is, actually, I want to go back. I want to show it develop. Let's see the whole thing. I'm going to let it run. So, again, can't overturn. Table won't stop spinning. We're totally screwed. We have an awesome fluid gyroscope. So what's the fluid do? Can you guys see it? What's it starting to do? Tutorial, you can speak up. Come on. Yeah. It's making smaller cells. So how do you get friction to kick in a fluid? One way is you go to small scale. With fluids, friction is scale dependent. So you can think of it like a boba straw versus a coffee stirrer, right? Try to drink your coffee through a boba straw. One, you'll burn your mouth, but two, it's incredibly easy to suck the fluid through a big fat straw. Now try it again with a coffee stirrer. You'll burn your mouth less because you can't suck anything through a skinny straw because friction is scale dependent. So that's what the fluid does as well. It chooses and selects a small enough scale where it can break the rotational constraint. And if you look, yeah, okay, that's nice. Great. Yeah. And if you look, what you're seeing, all these little cells are really just self-similar helical cells similar to what we saw with our slowly rotating tomato can. And so there is, of course, a difference. I don't have a tomato can, but you'll see these dark spots in the middle of each cell. That is the central dense downwelling. So each little dark spot kind of is your quote-unquote tomato paste can. Does that make sense? That's the cold stuff, and as it sinks down, it swirls one way at the top, swirls the other way at the bottom. So we saw our solution, large scale, with our tomato can, and now we're seeing we form a myriad such structures in a real freely rotating, freely evolving fluid. And here it is close up. You can say, oh, what the heck is that big wave? That big wave is really hard to level a rolling table for outreach. So we leveled it, but not perfectly. And so then you get this beautiful free mode. Not what we want, but it doesn't really change our story. And I think you can see, there's our solution, and there's the solution for rotating convection that's on the cover of Chandrasekhar's treatise. And it's the same thing. Big swirling flow, swirling in at the top, and then diving down. That's just what Chandra gets. In addition, it's also what you see in the rotating convection and really the dynamo models too. Little swirls below the swirl, a downwelling. And you might say, oh, these are super tall. Yes, the more rapid the rotation or the weaker the viscosity, the skinnier the length scale has to get in laterally, right? You just have to shrink down till this matters. Okay, so I think you can see these structures a little better if I bust out my iPhone and just take an image from a movie from the lab. So that's what you see with this rotating device. I think you can see lots of these structures in 3D, but each one is this beautiful little localized helix. Make sense? Okay. Awesome. If we look from the side, GoPro on the side of the tank, let's speed it up. All these little helices, you can see them helicizing all the way down through the layer, if helicizing is a word. Okay. Yeah. So, okay, so the faster we would rotate, again, the smaller the lateral size of the cells, and the more anisotropic the solution would get. But everything's self-similar. It's always really the same thing in this case, in this simple example. So what I've done today is just try to give a really simple heuristic model of why we see what we see, and why you hear people when they talk about quasi-geostrophic, which just means rapidly rotating, quasi-geostrophic solutions in these dynamo models, and why you hear people saying, oh, everything's aligned in these dynamo models. This is why. Okay, and I hope you get that. What else can I tell you? Summary, rotationally constrained core flow. There it is. Really skinny structures necessary to break the gyroscopic constraint imposed by rapid rotation. And the flow then becomes axialized. What I haven't gone into here is, if the flow is strongly anisotropic and really paying attention to that rotation axis, then it's these flows in the core that also are generating the magnetic field, and they will, on average, tend to generate axially aligned magnetic fields. That ties all the way back to my first slide where I said, oh, what a nice aligned magnetic field we have. That's due to this rotational alignment. Okay. Open questions that I've heard discussed this week at the meeting. What are the dominant drivers of core flow? I said, oh, it's intercore formation. It possibly is. There's also the idea that you could have buoyancy being released at the core mantle boundary. So it could be from above or below. Open question. Flow scale. What I've said is it's these little columns, and if you asymptote that to how fast Earth's core is apparently rotating or non-dimensionally rotating, these would be immensely skinny structures. And some people argue that, no, it's got to be larger structures. Maybe there's storms down there. There's lots of dynamics in the magnetic field, and maybe there's large-scale dynamical structures as well. Really an open question. I've heard people discuss magnetic scale structures versus flow structures. Are they related? Are they one-to-one? A lot of times we make them one-to-one in the models, but they don't have to be in a liquid metal. How stormy is core weather, and what drives all the spatio-temporal variations we see in the field? That is still, to me, very open for argument. And lastly, what are the importance of boundary processes? I had a very simple, clean system, but in Earth's core, there's probably lots of heterogeneity on all the boundaries, and that could actually be what's inducing this possible stormy weather. So, lots of open questions. I've done the simplest thing I could and just explained the fundamental flow that we see in these models. I want to thank a lot of people who gave me material. Joule, John Chang made that schematic of the core. Chris Finlay made a new movie of the magnetic field on Sunday. Thomas Gastine, Henry Gonzalez built the table. Susanna Horn sent images. Rob Long sent images. Taylor helped build the table and do experiments with me. And Andrei Shako sent movies too. And then in the lab while doing these experiments, people helped me as well. That is the cleanup and pit and enthusiasm crew. So thanks all around, and thank you for coming to this tutorial in AGU's 100th year. Thanks very much. If you have any questions, go ahead and ask. Thank you. If you have any questions, go ahead. Since I'm chair as well, you can just ask. Pierce, what do you got?
Yeah, so at the beginning you showed the magnetic field at the surface.
Yeah.
And then at the core mantle boundary.
Yes.
And the core mantle boundary looked a lot messier.
Yeah.
So what cleans it up by the time it gets to the surface?
It's a potential field, so there's no currents in the mantle at 0th order. So if there's no currents, then all the fields are emanating from the core, and then they're falling off as potential fields do, in this case, for magnetic fields, at least as R cubed. So, and then as you go up to higher harmonics, they're falling off as R4th, R5th. So the smallest scales fall off fastest, and you can see best the dipole field at the surface. There's lots of other data, but the dipole's crushing everything at the surface. But the data's there, it's just very weak. And so then when you invert back to the source region, you see a lot more structure. You can't go inside the core because that's where the currents are. And so you can't potential field invert any deeper. Does that make sense? Awesome. Any other questions? I love that. Okay, well, thank you again. And I believe I'll end this session. I'll thank the speaker one more time, and we'll call it a day at that.